The first hints of artificial origin emerge not through dramatic technological revelations, but in subtle structural anomalies that distinguish 3I Atlas from typical natural objects formed through conventional astrophysical processes. Density measurements reveal internal architecture that appears too organized, too precisely stratified to result from random accretion or gravitational sorting, suggesting engineered mass distribution designed to optimize structural integrity during millions of years of interstellar acceleration and cosmic ray bombardment. High-resolution imaging reveals surface features with geometric regularities that exceed the statistical expectations for natural weathering and impact processes, including linear formations, angular boundaries, and symmetrical structures that could theoretically represent manufactured components or technological systems concealed beneath layers of cosmic dust and radiation, processed surface materials that accumulated during prolonged interstellar exposure. Spectroscopic analysis detects trace element distributions that violate natural abundance patterns expected for objects formed through stellar nucleosynthesis and planetary accretion processes. With systematic enrichments in rare Earth elements and isotopic ratios that suggest artificial concentration and purification processes that operated according to technological rather than astrophysical principles during the object's formation. Thermal emission patterns exhibit systematic variations that could indicate internal heat sources or energy distribution systems operating according to engineered rather than natural thermal transport mechanisms, with temperature gradients that suggest directed energy flow through designed pathways rather than simple thermal conduction through homogeneous materials that characterize natural cosmic objects. Rotational dynamics reveal anomalous characteristics, including non-principal axis rotation and complex tumbling behaviors that could theoretically result from a symmetric mass distribution designed to optimize orientation control and communication system pointing during interstellar cruise phases, creating rotational signatures that distinguish artificial from natural objects through engineered rather than chaotic dynamical evolution. Only took advanced observational techniques a few decades to achieve sensitivity sufficient for detecting subtle artificial signatures that might distinguish manufactured objects from natural cosmic bodies. Yet such technological artifacts could theoretically remain unrecognized for centuries without systematic analysis, designed specifically to identify engineering signatures rather than conventional astrophysical characteristics. Material property analysis reveals mechanical strength characteristics that exceed theoretical expectations for natural cosmic materials subjected to millions of years of thermal cycling and radiation damage, suggesting composite structures or engineered materials designed to maintain structural integrity under extreme environmental conditions that would destroy conventional natural assemblages over geological timescales. Electromagnetic signatures include systematic variations in radio frequency emissions and reflection characteristics that could theoretically represent engineered electromagnetic properties designed for communication, navigation, or stealth applications rather than natural electromagnetic responses that reflect simple material composition and surface texture characteristics. Chemical stability indicators suggest resistance to space weathering and cosmic ray degradation that exceeds natural material capabilities, potentially indicating engineered surface treatments or protective systems designed to preserve functionality during prolonged interstellar exposure to radiation fields and micrometeorite bombardment that would alter natural surface composition over cosmic timescales. The mystery of observational subtlety emerges from recognition that advanced technological artifacts might be designed to appear natural to primitive observation techniques, while concealing artificial characteristics that become apparent only through sophisticated analysis methods that exceed the technological capabilities of species in early stages of astronomical development. Comparative analysis with known natural objects reveals systematic deviations in multiple observable characteristics that collectively create statistical signatures inconsistent with natural formation processes, yet individually remaining within ranges that could be attributed to normal variation in cosmic object properties without comprehensive multivariate analysis designed to identify artificial origins. Structural coherence measurements indicate internal organization that maintains geometric relationships and material distributions despite millions of years of thermal cycling and mechanical stress, suggesting engineered designs that account for long-term structural evolution under interstellar conditions rather than natural accretion that creates randomly organized internal architecture. Surface modification patterns exhibit systematic characteristics that could theoretically represent controlled ablation or engineered erosion designed to reveal internal systems or modify external appearance according to predetermined schedules rather than random space weathering that creates unpredictable surface evolution over cosmic timescales. Information theoretical analysis of structural and compositional patterns reveals organizational complexity that exceeds expectations for natural processes while approaching levels that could theoretically encode information through systematic arrangements of materials, isotopic compositions, or structural configurations that preserve data through physical rather than electronic storage mechanisms. Statistical anomaly detection algorithms identify correlations between multiple observable characteristics that create signatures inconsistent with natural formation scenarios, yet potentially explicable through artificial origin, hypotheses involving deliberate engineering design that optimizes multiple functional requirements simultaneously through integrated technological solutions. Future analysis techniques will employ increasingly sophisticated pattern recognition and anomaly detection methods to identify artificial signatures that might distinguish technological artifacts from natural cosmic objects, while developing new theoretical frameworks for recognizing engineering characteristics that operate according to design principles potentially unknown to human technological experience. The implications of potential artificial origin extend beyond scientific curiosity to encompass fundamental questions about technological evolution, cosmic civilization development, and the possibility that interstellar space contains archaeological artifacts from extinct extraterrestrial intelligence that achieved technological capabilities exceeding current human spaceflight technology before disappearing from the cosmic stage millions of years ago. The archaeological investigation of 3I Atlas's internal structure employs techniques borrowed from terrestrial archaeology and materials science to search for evidence of manufacturing processes, technological components, and engineered systems that might be preserved within the object's matrix, despite millions of years of cosmic exposure and potential deliberate concealment designed to disguise artificial origins from primitive detection methods. X-ray tomography and neutron imaging reveal internal density variations and structural organizations that could theoretically represent technological systems embedded within protective matrices designed to survive interstellar transport while maintaining functional integrity over geological timescales. Crystallographic analysis detects artificial isotope separation and chemical purification signatures that suggest technological processing rather than natural nucleosynthesis and stellar formation processes. With systematic enrichments in specific isotopes and trace elements that could theoretically result from advanced materials engineering designed to optimize structural, electronic, or nuclear properties for technological applications rather than random chemical evolution through astrophysical processes. Microscopic examination reveals structured materials with organized arrangements at molecular and atomic scales that exceed the complexity expected from natural crystallization and chemical self-organization processes, potentially indicating nanotechnological manufacturing techniques that create precisely controlled material architectures through atomic-scale engineering that operates according to design principles rather than thermodynamic equilibrium and chemical kinetics. Composite material identification reveals systematic associations between different phases and components that suggest engineered rather than natural formation processes, with material combinations that optimize multiple physical properties simultaneously through deliberate design choices rather than accidental chemical associations that result from conventional geological and astrophysical evolution under random environmental conditions. Inclusion analysis detects microscopic objects with geometric forms and systematic internal structures that could theoretically represent manufactured components or technological devices embedded within protective matrices, including spherical, cylindrical, and polyhedral forms with internal organization that suggests functional design rather than natural crystal growth or accidental aggregate formation through cosmic dust accretion. Only took advanced materials analysis techniques a few decades to achieve resolution sufficient for identifying artificial structures and manufacturing signatures at microscopic scales. Yet such technological archaeological investigation requires systematic analysis designed specifically to recognize engineering characteristics rather than conventional geological and cosmochemical processes that dominate natural object formation. Trace element mapping reveals systematic spatial distributions that could indicate technological systems or information storage architectures embedded within the object's structure, with element concentrations and isotopic ratios that vary according to organized patterns, rather than random distributions expected from natural chemical evolution and cosmic ray bombardment effects that typically homogenize trace element compositions. Interface boundary analysis between different material phases reveals systematic relationships and contact geometries that suggest engineered assembly processes rather than natural phase separation and chemical segregation, with interface characteristics that optimize mechanical, thermal, or electronic properties through deliberate design choices rather than accidental material associations created through natural processes. The mystery of preservation mechanisms emerges from recognition that technological components and manufacturing signatures must survive millions of years of cosmic ray bombardment, thermal cycling, and chemical alteration that would typically destroy artificial materials and erase evidence of technological origin, unless specifically designed to resist such environmental degradation through advanced materials engineering. Functional system identification attempts to recognize technological components that could theoretically serve specific engineering functions including energy storage, information processing, communication, navigation, or structural support, requiring analysis techniques that can distinguish between accidental material arrangements and deliberate functional designs that operate according to engineering principles. Exotic matter detection searches for materials with properties that exceed natural formation capabilities and suggest advanced technological synthesis, including metamaterials with engineered electromagnetic properties, programmable matter with variable characteristics, or quantum materials that exploit fundamental physical principles for technological applications unknown to current human engineering capabilities. Manufacturing signature analysis looks for evidence of artificial production processes including machining marks, assembly interfaces, quality control variations, or systematic production characteristics that distinguish manufactured objects from natural formations through analysis of surface textures, internal structures, and material property distributions that preserve evidence of technological origin. Technological timeline reconstruction attempts to determine when artificial components were manufactured and assembled through radiometric dating of technological materials. Analysis of cosmic ray exposure effects on engineered systems, and correlation with theoretical technological development pathways that could produce the observed artificial characteristics through extraterrestrial engineering evolution. Reverse engineering approaches attempt to understand potential technological functions and design principles through analysis of structural arrangements, material properties, and systematic organizations that could theoretically serve engineering purposes, requiring interdisciplinary analysis that combines materials, science, engineering design principles, and speculative technology assessment. Information encoding detection searches for systematic patterns in material arrangements, isotopic compositions, or structural configurations that could theoretically encode information through physical storage mechanisms that preserve data through material arrangements rather than electronic or magnetic storage systems vulnerable to cosmic radiation and electromagnetic interference. Comparative technological analysis evaluates whether observed artificial characteristics represent technological capabilities that exceed current human engineering while remaining consistent with theoretical limits imposed by fundamental physical principles, providing frameworks for assessing the technological sophistication of potential extraterrestrial manufacturing processes. Future archaeological investigation will employ increasingly sophisticated analytical techniques including atomic-scale imaging, quantum material characterization, and artificial intelligence pattern recognition to identify technological signatures while developing new, theoretical frameworks for recognizing engineering principles that might operate according to design philosophies unknown to human technological experience. The implications of successful technological archaeology extend beyond confirming artificial origin to encompass fundamental insights into extraterrestrial engineering capabilities, technological development pathways, and design philosophies that could reveal how advanced civilizations approach interstellar exploration and information preservation over cosmic timescales that exceed biological species' lifetimes. The trajectory analysis of 3I Atlas reveals subtle anomalies that suggest deliberate navigation and course corrections rather than passive gravitational evolution, with orbital characteristics that indicate possible targeting of specific stellar systems or galactic regions through controlled propulsion events that occurred over millions of years of interstellar cruise. Precise astrometric measurements detect systematic deviations from purely ballistic motion that could theoretically result from periodic thrust events generated by onboard propulsion systems designed to maintain or adjust trajectory toward predetermined destinations across galactic distances. Non-gravitational acceleration patterns exhibit systematic characteristics that differ from typical cometary outgassing or radiation pressure effects, with acceleration vectors that maintain consistent orientations relative to galactic coordinates rather than solar-centric directions that characterize natural forces acting on cosmic objects. These acceleration anomalies suggest possible reaction control systems or exotic propulsion technologies that operate according to program navigation sequences rather than environmental responses. Approach geometry analysis reveals trajectory characteristics that maximize observation opportunities and communication windows with Earth during solar system passage, potentially indicating deliberate timing and course planning designed to optimize scientific data collection or communication attempts during brief encounters with technological civilizations. The specific approach angle and velocity could theoretically result from navigation planning that accounts for Earth's orbital motion and technological development timeline, Galactic motion correlation indicates trajectory characteristics that remain consistent with specific galactic coordinates and stellar motion patterns over millions of years of interstellar travel, suggesting navigation systems that maintain course relative to galactic reference frames rather than local stellar systems that would create trajectory drift and course deviation over cosmic timescales without active navigation corrections. Precision requirements for achieving observed trajectory characteristics exceed statistical expectations for random gravitational encounters and cosmic accident scenarios, indicating possible deliberate targeting that requires navigation accuracy, measuring fractions of degrees over interstellar distances and millions of years of travel time through gravitational environments that include stellar encounters and galactic rotation effects. Only took sophisticated orbital analysis a few decades to achieve precision sufficient for detecting subtle trajectory anomalies that might distinguish controlled from natural motion. Yet such navigation signatures could remain unrecognized without systematic analysis designed to identify artificial course corrections, rather than conventional gravitational and environmental forces that dominate natural object motion. Velocity vector optimization appears designed to maximize encounter duration and observation opportunities while minimizing approach velocity to enable extended data collection periods during solar system passage, suggesting mission planning that balances scientific objectives with propulsion system capabilities and fuel efficiency considerations over interstellar distances. Stellar encounter history reconstruction reveals trajectory evolution that avoids close approaches to massive stars and gravitational hazards that could disrupt controlled motion or damage technological systems, potentially indicating navigation planning that accounts for galactic environmental hazards and maintains safe operating distances from high radiation stellar environments during millions of years of interstellar cruise. The mystery of propulsion system concealment emerges from recognition that deliberate navigation requires energy sources and reaction mass that might remain undetectable using conventional observational techniques if propulsion technologies operate according to exotic physical principles or employ extremely efficient systems that minimize observable signatures. Course correction timing analysis reveals systematic patterns in trajectory modifications that could theoretically correspond to predetermined navigation schedules or responses to astronomical events including stellar encounters, galactic environmental changes, or approach phase requirements that optimize mission objectives through programmed navigation sequences. Target selection implications suggest trajectory characteristics that could indicate deliberate selection of solar system encounter based on astronomical observations of planetary characteristics, technological development indicators, or stellar system properties that identify Earth as potentially interesting target for scientific investigation or communication attempts. Multi-phase navigation evidence includes trajectory segments that suggest different navigation objectives during various phases of interstellar travel, potentially indicating mission plans that evolve over cosmic timescales in response to changing galactic environments. Technological system degradation, or updated target assessment based on improved astronomical observations. Communication geometry optimization reveals approach characteristics that maximize radio frequency communication opportunities and minimize interference from solar radiation and planetary motion, suggesting mission planning that accounts for electromagnetic propagation effects and communication system limitations during brief encounter windows with potential technological civilizations. Orbital mechanics modeling demonstrates that achieving observed trajectory characteristics requires navigation capabilities that exceed current human spaceflight technology, while remaining consistent with theoretical propulsion systems based on advanced physics including fusion rockets, antimatter drives, or exotic matter propulsion that could theoretically provide sufficient performance for controlled interstellar navigation. Encounter prediction accuracy suggests navigation systems capable of predicting solar system conditions and planetary positions over millions of years of travel time, indicating computational capabilities and astronomical knowledge that exceed current human predictive accuracy for long-term celestial mechanics and galactic environmental evolution. Future trajectory analysis will employ increasingly sophisticated orbital determination techniques and gravitational modeling to characterize navigation signatures while developing theoretical frameworks for recognizing artificial course corrections that operate according to propulsion technologies and navigation principles potentially unknown to current human spaceflight experience. The implications of deliberate navigation extend beyond confirming artificial origin to encompass fundamental insights into extraterrestrial spaceflight capabilities, mission planning methodologies, and technological approaches to interstellar exploration that could reveal how advanced civilizations conduct scientific investigation and communication attempts across galactic distances and cosmic timescales. The crystalline matrices within 3I Atlas exhibit organizational patterns that transcend natural geological processes and suggest systematic information encoding schemes where atomic arrangements, isotopic distributions, and molecular configurations could theoretically store vast amounts of data through three-dimensional crystallographic libraries that preserve information across millions of years of cosmic exposure. Advanced crystallographic analysis reveals systematic structural patterns that exceed the complexity expected from natural crystal growth, while approaching organizational levels that could theoretically encode encyclopedic databases within physically stable storage media designed to survive interstellar transport. Molecular memory systems within organic components demonstrate systematic arrangements that could theoretically function as chemical storage devices where specific molecular sequences, stereochemical configurations, and chemical bonding patterns preserve information through biochemical encoding schemes, analogous to DNA data storage yet optimized for extreme environmental conditions, including cosmic radiation, temperature cycling, and chemical degradation over geological timescales. Isotopic encoding possibilities emerge from systematic variations in isotope ratios that exceed natural nucleosynthesis patterns and suggest artificial isotope separation, designed to create information storage systems where different isotopic compositions represent data bits or encode complex information through nuclear arrangements that remain stable over cosmic timescales, despite environmental perturbations that would destroy electronic or magnetic storage systems. Quantum storage mechanisms could theoretically operate through controlled quantum states preserved in crystalline defects, trapped atoms, or metastable nuclear configurations that maintain quantum information through physical protection mechanisms designed to isolate quantum systems from environmental decoherence, while preserving quantum data encoding schemes that exploit fundamental physical principles for ultra-high-density information storage. Hierarchical organization patterns reveal systematic relationships between molecular, crystalline, and structural scales that suggest nested information architectures where data encoding operates simultaneously across multiple organizational levels, from atomic arrangements through macroscopic structural patterns, creating redundant storage systems that preserve information integrity despite partial degradation or damage to individual storage components. Only took information theory a few decades to recognize that physical matter could theoretically serve as information storage media with densities that exceed electronic systems by enormous factors. Yet, developing practical techniques for encoding and retrieving information from crystalline and molecular storage systems remains challenging even for current human technology with controlled laboratory conditions. Error correction signatures within systematic patterns suggest redundant encoding schemes and self-correcting information architectures designed to maintain data integrity, despite cosmic ray damage and environmental degradation that would introduce errors in stored information, potentially indicating advanced information theory applications that exceed current human error correction capabilities. Storage density calculations indicate that observed organizational complexity could theoretically encode information quantities measuring exabytes, or larger within volumes measuring cubic centimeters. Creating information storage densities that exceed current human technology by factors of millions, while maintaining stability over cosmic timescales that exceed technological civilization lifetimes. The mystery of information retrieval mechanisms raises questions about how encoded information could be accessed and decoded by technological civilizations that encounter storage systems, potentially requiring specific technological capabilities, decryption keys, or analytical techniques that enable information extraction from physical storage media without destroying encoded data. Multi-scale encoding evidence suggests information storage systems that operate across different physical scales simultaneously, with macroscopic structural patterns that provide access keys or indexing systems for microscopic data storage, while creating hierarchical information architectures that optimize both storage density and retrieval efficiency through systematic organizational principles. Chemical stability analysis indicates information encoding systems designed to survive specific environmental conditions, including cosmic radiation, temperature extremes, and chemical exposure, while maintaining information integrity over timescales that exceed biological species evolution, suggesting storage technologies optimized for interstellar transport and long-term preservation. Pattern recognition algorithms applied to structural and compositional data reveal systematic correlations that exceed statistical expectations for random arrangements, while approaching complexity levels that could theoretically represent encoded information, language patterns, or mathematical relationships that preserve knowledge through physical arrangements rather than conventional information technology. Cryptographic implications suggest that encoded information might require specific decryption methods or technological keys that prevent unauthorized access, while enabling information retrieval by civilizations that achieve appropriate technological sophistication. Creating information security systems that operate through physical rather than computational protection mechanisms. Content speculation based on storage capacity and organizational complexity suggests potential information categories, including star charts, scientific databases, historical records, cultural archives, or technological blueprints that could theoretically be preserved within physical storage systems designed to transmit knowledge across galactic distances and cosmic timescales. Access methodology development requires interdisciplinary approaches that combine crystallography, molecular biology, information theory, and speculative technology assessment to develop techniques for potential information extraction from physical storage systems while avoiding damage to irreplaceable archaeological artifacts that might contain unique records of extraterrestrial civilization. Verification protocols would enable confirmation that systematic patterns represent genuine information encoding rather than natural organizational complexity or human pattern recognition biases, requiring statistical analysis and theoretical frameworks that can distinguish between accidental complexity and deliberate information storage through quantitative measures of organizational sophistication. Future information archaeology will employ increasingly sophisticated analytical techniques, including quantum state measurement, molecular sequence analysis, and artificial intelligence pattern recognition, to identify and potentially decode information storage systems while developing new theoretical frameworks for recognizing and interpreting physical information, encoding schemes that operate according to principles potentially unknown to human information technology. The implications of successful information storage identification extend beyond confirming artificial origin to encompass unprecedented opportunities for accessing extraterrestrial knowledge bases that could contain scientific, historical, and cultural information from extinct technological civilizations, while providing insights into information preservation strategies and knowledge transmission methods that operate over cosmic timescales. The anomalous energy signatures detected within 3I Atlas's structure suggest the presence of artificial power generation systems that continue operating after millions of years of interstellar travel. With isotopic compositions and thermal characteristics that indicate exotic energy sources beyond conventional chemical, nuclear, or gravitational power systems that typically characterize natural cosmic objects. Radiometric analysis reveals systematic isotope ratios that suggest controlled nuclear processes or exotic matter interactions that generate energy through mechanisms unknown to current human physics, while maintaining stable power output over geological timescales. Thermal emission patterns exhibit systematic characteristics that exceed expectations for passive thermal equilibrium with cosmic microwave background radiation, suggesting internal heat sources that operate according to engineered rather than natural energy generation processes. The observed thermal signatures indicate possible controlled fusion reactions, antimatter annihilation, or zero-point energy extraction that maintains temperature gradients and energy flux patterns incompatible with natural thermal evolution over cosmic timescales. Exotic isotope detection reveals the presence of artificial radioactive elements with half-lives and decay characteristics that suggest technological synthesis rather than natural nucleosynthesis processes, potentially indicating isotope batteries or controlled nuclear systems that provide sustained power generation through engineered radioactive decay chains optimized for longevity and stable energy output during interstellar cruise phases. Magnetic field anomalies suggest internal current systems or magnetic field generation that require sustained electrical power and organized electromagnetic systems rather than natural magnetic remnants or temporary electromagnetic induction effects. These magnetic signatures could theoretically indicate superconducting power storage systems, magnetic field generators, or electromagnetic propulsion components that maintain active operation over cosmic timescales. Energy storage signatures within crystalline matrices suggest possible power accumulation systems, including exotic matter reservoirs, quantum energy storage, or controlled vacuum fluctuation harvesting that maintains energy reserves for operational systems while providing backup power for extended mission phases when primary power generation systems experience degradation or failure. Only took advanced physics a few decades to recognize theoretical energy generation mechanisms that could theoretically provide sustained power over cosmic timescales. Yet implementing such exotic energy systems remains beyond current human technological capabilities, while potentially representing standard engineering solutions for advanced extraterrestrial civilizations. Quantum vacuum signatures suggest possible zero-point energy extraction systems that harvest energy from quantum field fluctuations through mechanisms that remain theoretical in human physics, yet could theoretically provide unlimited power generation without fuel consumption or waste products that would compromise stealth characteristics during interstellar operations. Controlled fusion evidence includes systematic nuclear reaction products and neutron activation signatures that suggest sustained fusion reactions operating under controlled conditions rather than natural stellar nucleosynthesis or cosmic ray interactions, potentially indicating miniaturized fusion reactors optimized for long-term operation in cosmic environments. The mystery of power system maintenance emerges from recognition that energy generation systems must continue operating reliably over millions of years despite cosmic ray damage, thermal cycling, and component degradation that would typically destroy technological systems without sophisticated self-repair capabilities or redundant backup systems. Antimatter containment possibilities suggest energy storage or generation systems that utilize matter-antimatter interactions for power generation, while maintaining sophisticated containment systems that prevent accidental annihilation during cosmic transport through environments that include electromagnetic fields, cosmic radiation, and mechanical stress that could disrupt containment systems. Superconducting component evidence includes magnetic field patterns and electrical conduction characteristics that suggest superconducting materials or systems that maintain zero electrical resistance for efficient power transmission and magnetic field generation, despite temperature variations and cosmic radiation exposure that would typically destroy superconducting properties. Energy conversion efficiency analysis indicates power systems that operate with conversion efficiencies approaching theoretical limits imposed by fundamental physical principles, suggesting advanced engineering that optimizes energy utilization while minimizing waste heat and electromagnetic signatures that could compromise stealth characteristics during interstellar reconnaissance operations. Power distribution networks within the object's structure suggest systematic electrical or electromagnetic systems that distribute power between different components and operational systems while maintaining isolation and protection against cosmic radiation and electromagnetic interference that could disrupt power system operation. Backup power indicators suggest redundant energy generation and storage systems designed to maintain operational capability despite primary system failures or degradation over cosmic timescales, potentially including multiple independent power sources and automatic switching systems that ensure continued operation throughout extended mission phases. Stealth power management could theoretically minimize detectable energy signatures through sophisticated thermal management, electromagnetic shielding, and power system design that prevents energy leakage while maintaining operational capability for scientific instruments, communication systems, and navigation equipment during reconnaissance operations. Future energy system analysis will employ increasingly sophisticated detection techniques, including high-resolution spectroscopy, magnetic field mapping, and exotic matter detection to characterize power generation systems while developing theoretical frameworks for recognizing energy technologies that operate according to physical principles potentially unknown to current human physics. The implications of advanced power systems extend beyond confirming artificial origin to encompass fundamental insights into exotic energy generation technologies and engineering approaches to sustained power generation over cosmic timescales, potentially revealing energy technologies that could revolutionize human spaceflight capabilities and terrestrial energy systems while providing evidence of physics applications that exceed current theoretical understanding.